Assalamualaikum. My name is Azrin Iqbal bin Muhammad Badruddin. Today I'm going to share about the introduction of our project. Many industrial and mechanical processes include the control system, and controllers are the essential elements that enable these systems to function. There are various distinct kinds of controller, each with special qualities and skills of their own. Three of the most popular controllers, the proportional P, proportional integral PI, and proportional integral derivative PID controllers will be the subject of this research. The three types of the controllers is proportional. A proportional controller P is a type of control system that adjusts the output in proportion to the error between the desired set point and the current value. It operates by calculating the error signal and multiplying it by a constant gain to determine the control action. Next, as for the proportional integral (PI), a proportional integral (PI) controller is an extension of the proportional controller, adding an integral term to the control equation. The integral term helps to eliminate residual error in the system and improve the stability of the control loop. Lastly, for the proportional integral derivative (PID), a proportional integral derivative PID controller is a further extension of the PI controller, adding a derivative term to the control equation. The derivative term helps to predict future error and prevent overshoot and oscillation in the control loop. In summary, a PID controller is a combination of proportional, integral, and derivative control, providing improved control and stability compared to P or PI control. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman bin Muhammad Sufyan and my matrix number is 2040. So for the methodology part, we frequently employ the PID controller in the power system to restore the frequency, to restore the voltage and other parameters to its initial values. However, as we know, tweaking the PID controller is quite difficult, so the time-consuming hit and try approach is widely used. So we use the MATLAB Simulink model because the recent version of the MATLAB software have included the PID tuner, which only requires that we input the response of any Simulink model and they will instantly return us within a brief period of time. So in order to create an open loop and closed loop system, we first need to add the second order transfer function to the model in the MATLAB Simulink function, Simulink software. So for P, PI, and PID controller as well as open loop model system, a different transfer function was applied for each model. Then we just open the dashboard to bring up the blank window which function as a scope and display the graph without opening the scope. And then after we run the simulation, the graph displayed a significant overshoot and a very long settling period. Then we just need to tune it precisely using the PID tuner to eliminate the overshoot and a brief settling period. To launch the PID tuner, we need to click the button on the PID controller block. The PID tuner will launch and then transmit the graph there and instantly will create a tune control response for the graph. The new parameter value is displayed in the controller parameter. It displays several block and tune response parameters so that the result can be compared. So after the simulation, after the PID controller produces a satisfactory outcome, the next part is to design an open loop system using a different transfer function. Open loop system does not require to use PID tuner because the open loop system serves as a direct transfer function, giving the user the desired graph right away. Thank you, that's all from me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nazias Bibi Osman and my matric number is CE21002C. I will explain for the simulation part. So based on the instruction, we have to design a P, PI and PID controller for a closed loop system with appropriate system requirement for transient response by tuning the controller using Simulink. So as you know, a proportional integral derivative, which means PID controller is a control loop mechanism employing feedback that is widely used in an industrial control system and a variety of other applications requiring continuously modulated control. So first of all, this is the circuit that we produce using the Simulink. The component that we use is step, sum, PID controller, transfer function, and scope to produce a graph. So this is the manual tuning simulation that we produce using a MATLAB. So first of all, we have to run the simulation. So the circuit has simulated. After that, we have to click scope to produce a graph. So this is the graph for the manual tuning. First of all, we have to click the cursor to find the value for rise time and the overshoot and value and peak. So you have to plot the cursor at the high value, which is this, and then we measure signal statistic and level measurement. As you can see the value for the rise time, peak and overshoot. So this is the value for the manual tuning. So but we have complete the result, which is the rise time that we get is 0.18639 second, and for the settling time is 2.68 second. For the overshoot 8.152%, and for the peak is 1.082. And then for the auto tune, so this is the auto tune circuit. So we have to run the simulation. Click scope. So this is the graph for the auto tune circuit. Just same for the previous procedure, you have to click the cursor measurement to find the value for the rise time, overshoot and peak. So on signal statistic and by level measurement. So you can see the value for the peak, rise time and overshoot. So this is the result that we get, which is for the auto tune for the rise time is 0.031006 second, and for the settling time is 0.243 second, and for the overshoot 17.059%, and for the peak is 1.168. So that's it for the closed loop PID. Next is closed loop PI manual tuning. So this is the closed loop PI manual tuning. So first of all, we have to run the simulation. So the circuit has simulated, and then you have to click scope to find a graph. So this is the graph for the manual tuning. So and then you have to click the cursor measurement. So plot the cursor at the high value of the graph. So measurement, signal statistic, measurement, B-level measurement. So you can see the value for the peak, rise time, and overshoot. So this is the result that we get for the closed loop PI for the manual tuning. For the rise time that we get is 0.16112 second. For the settle time is 2.87 second. For the overshoot is 34.459%, and for the peak is 1.346. So the next is for the auto-tune. So this is the circuit for the auto-tune. So firstly you have to run the simulation. So the circuit has simulated. So you have to click scope to find graph. Click cursor. Measurement, signal statistic. So based on the graph, you can see the value for the peak, rise time, and overshoot. So the result that we get for the auto-tune is for the rise time 0.010463 second, and for the settle time is 0.087 second, and for the overshoot is 25.949%, and for the peak is 1.250. Next is for the closed loop P manual tuning. So this is the circuit for the closed loop P. So first of all, we have to run the simulation. And then click scope. So this is the graph for the closed loop P First of all, you have to click cursor. And then click measurements in a statistic. Measurement, deliver measurement. So you can see the value for the peak, rise time, and overshoot. So the next is auto tune. So this is the circuit for the P auto tune. So you have to run the simulation. So the circuit simulate and then click scope. Cursor measurement. So this is the value for the peak and the value for the rise time and the value for the overshoot. So the result that we get from the circuit for the P, for the closed loop P, which is for the rise time on the manual type is 0.173295 second, and for the static time is 2.35 second, and for the overshoot is 25.945%, and for the peak is 1.241, and for the auto tune for the rise time is 0.112871 second. For the static time is 1.23 second, for the overshoot is 21.341 second, and for the peak is 1.200. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Darwish bin Motauddin and my metric number is DE2030C. So we are group 5. We do this assignment with using a 140 kHz with using a MATLAB software.
Okay, Assalamualaikum. My name is Azrin Iqwan bin Muhammad Badruddin. Today I'm going to show the simulation of question 1. Firstly, for the question 1, we need to declare sims Tn. Then we need to declare frequency of our group, which is 140 kHz. Next, we need to declare the period, which is 1 over frequency, and declare the AO, which is 1 over 2. Next, we have to declare the AN that we got 1 over pi square times n square times negative 1 square n minus 1. Furthermore, we need to declare the Bn, and the Bn we got negative 1 over pi n. Lastly, we need to show the time interval, which is t equals to 0 and 0.000001 and 20 exponents 10 minus 5. So we need to run and we got the simulation. Now for the harmonic plot. Firstly, we need to put the frequency, which is 140 megahertz, and the period, which is 1 over frequency. We declare the AO, AN, BN, and time interval. Next, we need to declare the time domain for harmonic 5, and we got the simulation, the coding with the plot of t x t1 and subplot of 3, 1 and 1. Now for the time domain for harmonic 10, For the harmonic 10, we assume the value of R 100 ohm, and value of C calculate manually in F, which is 2.842 exponent negative 9, and impulse response of the low pass filter. Now we using the Bode plot for the low pass filter. This is the coding for the harmonic 10. As for the time domain for harmonic 20, we just do the same thing, just change the domain for 20 harmonic, and then we run. We got the HS, which is 1 over 2.842 exponent negative 7 s plus 1, and this is the figure for the amplitude time domain for 5 harmonic, time domain for 10 harmonic, and time domain for 20 harmonic. That's all from me. Thank you.
Okay, my name is Nur Fasha binti Muhammad Rashid. I will present for the frequency domain. Okay, this is coding for 5 harmonics of a frequency domain. This is coding for frequency domain 10 harmonics, and this is frequency domain for 20 harmonics. For this is our result. Thank you.
Hi, Assalamualaikum. My name is Nadira Adiba binti Jusuf. So this is the coding for filter from question 1. So we assume the value of R is equal to 100 ohm. Then we run the simulation. This is the result for filter. Next, for question 3, this is the coding, which is our group frequency was 140 kilohertz. Then we run the simulation. This is the result for question 3. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aiman Muhammad Sufian, and this is question 3 for frequency domain. So this is the coding. Fs is equal to 500 exponent 7, n equals to 10, Fc equals to 560 e exponent 6, and then this is the coding, and then we just click the simulation button, and this is the result. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Darush bin Mutawaddin, and my metric number is DE 2036. So this is the coding for question 3 time domain. So we can see this is the filter return to discrete time filter object, butterworth low pass filter design using the design low pass, and this is the all of frequency values are in a hertz, and this is a construct F design object and call its pattern method, and this is a EOF. This is the coding. So let's run. So this is the graph that we get from this coding. So that's all from me. Thank you very much. Bye bye.
Assalamualaikum. My name is Nur Fasha binti Muhammad Rashid. My matrix number is CE21069. I will present for the conclusion. The MATLAB Simulink software tool was used to model system using step, sum, PID controller, transfer function, and scope blocks. Open loop controls is simple and inexpensive, while closed loop control require feeding back position information to a motion controller. P controller are used to stabilize unstable first order process and reduce all system steady state error. The PID controller is used to eliminate the P controller steady state error, but it has a negative impact on response time and overall system stability. To eliminate overshoot and oscillation, a derivative gain component must be used in addition to the PI controller. The PID controller has the advantage of being able to be used with higher order process that require more than one energy storage.